Welcome, class, to part 2 of chapter 13, wherein we will be talking about concentration units. So in our previous lecture, we were discussing the basic definitions of solution, solubility, a little bit review, a little bit new. And today we're going to get into quantifying those properties a little bit. Namely, we're going to be talking about how we keep track of the amount of solute inside of a given amount of solvent. Now, we've already talked about one such unit before, the unit of molarity. So this should hopefully be review from our fall semester as well as a little bit of the spring semester. So for those who may not remember, or you just weren't in class last fall, which is totally fine, the molarity of a solution can be found by observing the amount of solute we have in the solution per a given volume in liters of the solution. So we can see in the equation below, which represents molarity, the amount of solute that we're finding goes into the numerator of our equation. The volume of our total solution is going to go into the denominator here. Now, molarity is going to be represented with the unit of molarity, or capital M. Sometimes molarity is also represented in moles per liter instead of the capital M. So both of these two, the capital M after some value, like let's say you're working with a 3.00 molar solution, this capital M is synonymous with 3.00 moles per liter, where again the moles are specifically the solute's number of moles, and this is per every liter of solution that we have. Now, the downside of molarity, which we haven't really faced that much up until this point, is that molarity is a temperature-dependent measurement. The reason why we haven't really had any issues with this up until this point is we haven't really been working with concentration specifically at like freezing points versus boiling points. However, as we get into part 3 part 3 of chapter 13, and we're discussing more of these quantifiable solution properties, the properties that take place at the freezing point and boiling point are really going to need a special temperature-independent unit. Now, why molarity is temperature-dependent, we can actually ascertain before moving on to this new and fresh unit by observing our density plot here. Now, the plot that is present is the density curve of water, which is the most common solution or solvent that we work with, especially when working with aqueous solutions. And so we're observing the density of water as a function of temperature in this plot. Now, we can see that the freezing point of water at 0 degrees Celsius has a very different density than at the boiling point, which is at 100 degrees Celsius. So we have to ask ourselves why the density of water is changing so much. Well, if we're observing just a beaker of water, and again, this is liquid, it's not evaporating yet, we're not quite at its boiling point, the mass inside of this beaker should remain constant. Mass is constant. And we know that density is equal to a mass divided by volume. So if our mass is remaining constant, and yet we can see as we increase temperature from 0 degrees C to 100 degrees C, our density is falling, well, we can ascertain that this must be because the volume of our solution is increasing. Well, if the volume of our solution is increasing, then that must mean that the liter measurement in our molarity equation down here is also increasing, which means the overall molarity is going to be decreasing. Even though the same amount of solute is present, and even though the same mass of water is present, due to the fluctuating volume as a function of temperature, we're going to see the measurable concentration of our solution change. Well, this is not good. I mean, if you're not worried about temperature dependence, molarity is fine, but if you are concerned with temperature-dependent properties, we can't use molarity as a measure of concentration for our solutions. Instead, we're going to have to use this unit, this measure of molality. Now, the words molarity and molality are fairly similar, but they are not the same measured quantity. What molality is still an amount of solute that is going to be measured in moles. However, it is going to be divided by the mass of the solvent in the denominator instead of the volume of the solution. Now this change is again because the volume of our solution changes as a function of density. However, as we increase our temperature from 0 to 100 degrees Celsius, even though our density is changing, again, the mass is constant. So it doesn't matter what temperature we're at, the density is not going to have an effect on the molality. Therefore, molality is a temperature-independent measurement, and we're actually going to be able to use it to quantify and ascertain some of the properties of solutions that we've yet to talk about, and we'll get into in part 3. So in observing our equation here, we can see that molality is represented by the little variable or a lowercase m, not capital M. As well, it is not mass. So I know, we have lowercase m for mass already. The unit for molality is the same variable, it's the same letter, it's just a lowercase m. So we're gonna have to use context clues in order to really be able to tell whether or not we're working with a mass in some mass unit, or if we're working with molality in a lowercase m. And that's fine. I mean, the context clues are pretty obvious, like moving forward as we start looking at example problems and homework problems. So just be aware that the same variable is used, it's just not the same thing. Molality and mass are not the same thing. All right, the last thing that we need to talk about, though, before actually getting into observing molality, its commonalities with molarity, is to recognize the distinction in the denominators of our molarity and molality equation. Not just the fact that we're looking at something per liters versus per kilograms, but also that one label had liters of solution versus the other had kilograms of solvent. These labels also matter. Solution versus solvent. The mass, amount, and volume of your solution is going to be equal to the sum of the solute and solvent masses, amounts, and volumes. In other words, liters of solution is also not going to be synonymous even with liters of solvent. Solution and solvent are not the same things. If we're looking at an actual solution, which we can see kind of represented here, all of our little solvent particles are present. They have a mass, they're taking up space, and even though in some, let's say, very low or dilutely concentrated solutions, we may not have a lot of solute present, but it is still present. Therefore, the total mass of a solution is going to be equal to the mass of the solute plus the mass of the solvent, for example. Similarly, the volume of the solution would be equal to the volume of the solute and the volume of the solvent. And this may seem like a really nitty-gritty detail because most of the time we kind of assume that the solution and the solvent masses, amounts, and volumes are basically equal because solute doesn't actually take up that much space or occupy that high of a concentration in our solutions. However, when working at very low boiling or very low freezing points, very high boiling points, when looking at the difference between molarity and molality, this distinction is key. So we're going to need to keep in the back of our minds the labels present on certain masses, amounts, densities, concentrations are always going to have this solution versus solvent label, and we're going to need to acknowledge that the two are not synonymous. This could not be more apparent than in the type of example problem that we are about to solve together below, wherein this example problem we are asked to solve for the molality of a potassium chloride solution. It seems innocent enough. In the wording of the problem, we are told that the solution has a concentration of 4.70 molarity and has a density of 1.09 grams per milliliter. We are also told to assume 1 liters of solution. Now, this assumption we can always make in this type of problem when we are asked to interconvert between ratios of like masses to volumes or moles per volumes. Like anytime we're working with a ratio like molality, molarity, and density, we can always assume a given starting point even if it's not given to us. So what I'm saying is if you're working through this type of problem on our homework site or on a worksheet and a volume is not given to you, feel free to assume 1 liter of solution. Right, so this is going to be a fair game starting point no matter the example problem you're working on in the context of molalities, molarities, and densities. So if you would like to attempt this example problem on your own, feel free to pause the video. However, the problem can be a little tricky, and so we are going to approach this problem together straight away. So again, if you want to pause, feel free to pause, but I am just gonna keep rocking and rolling straight on through. All right, so we're asked to find molality. The first step is always to assess like what kinds of equations we have to work with, what the values are that are given in the problem. So we're asked to find molality. We're just going to gather some stuff that we know. So molality represented with a lowercase m is equal to moles of solute divided by kilograms of solvent. All right, so let's just keep looking in the problem, see if moles of solute or kilograms of solvent are explicitly given to us. We can see that we have a concentration, 4.70, with a capital M, where this capital M, again, represent moles of solute, per liter of solution, where I'm going to keep using SOL''N as shorthand for solution. So this isn't moles of solute or kilograms of solvent. So if we keep reading, we can see that we have a density of solution, where density is equal to mass divided by volume. And we're also told 1 liter of solution. So we are given, and I'm going to label this explicitly here, V of solution is equal to 1.00 liters. All right, and I'm labeling this V of solution for the same reason that we just discussed on the previous slide. It's going to be really useful and necessary to determine when you are observing solution versus solute versus solvent in this type of problem. All right, well, we can see in the wording of the problem, we are not given any moles of solute or kilograms of solvent explicitly, so we're going to have to go around and find them. We can find them using the rest of the information provided. So, for instance, if we're looking for moles of solute, we can see from the molarity concentration, there's also explicitly a moles of solute inside of this equation. We're given a big ol' capital M, and we are given liters of solution, so we can use the information in the wording of the problem to find the numerator that we're going to need to solve for molality. All right, so let's just plug in the values to our equation explicitly. I'll just do it in red over here. So 4.70 with a capital M is equal to moles of solute divided by the volume of solution present in liters, here, 1.00 liters of solution. And if we rearrange to solve for moles of solute, we'd find that the moles of solute are equal to 4.70 moles. And I'm going to say moles of KCl just to be explicitly clear about what moles we're looking at. All right, so now that we have found moles of solute, we can plug that into the numerator in our molality equation up above, 4.70 moles of KCl. But before finding the molality, we still need to find kilograms of solvent. All right, so we can see that we have a density equation. In this density equation, where we already know density and we already have a given volume, it seems like all we'd need to do is rearrange and solve for mass, right? This is a trap. Do not fall for this trap. Remember, just like before in chapter 12, when looking at unit cells, the density of the unit cell was equal to mass of unit cell divided by volume of unit cell. This density provided to us in the current problem is the density of the solution. Density of solution. Therefore, the mass provided is also the mass of the solution, and the volume in the equation is the volume of solution. The mass that we would rearrange and solve for in this problem is not the mass of the solvent, but rather is the mass of the solution. Now, this is still useful. We can use mass of solution to find mass of solvent, but they are not equal. They are not the same thing. All right, so let's take that first step though. Let's use the density equation to find mass of solution, which we can then in turn use to find mass of solvent. All right, so the density of our solution is 1.09 grams per milliliter. The mass of the solution is what we are looking for, mass of solution. And this is going to be divided by the volume of solution, which again is given to us. We've used it once already. We're just going to need to make sure that our units are all working together. So we can see density is given in grams per milliliter. I'm going to convert our volume of solution into milliliters as well. So 1 liter is equal to 1,000 milliliters. It's a pretty straightforward conversion. We can insert that into the denominator down below here, 1,000 milliliters. All right, so we can rearrange and solve for the mass of the solution. Let's see, mass of solution there is equal to 1,090 grams. All right, so again, this is not the mass of the solvent, but is the mass of the solution. And we know that the solution is equal to the sum of its parts, meaning the mass of the solution is equal to the mass of the solute, which we already know some stuff about, plus the mass of the solvent. If we can figure out the mass of the solute, then we can use this association, this relationship, to find the mass of the solvent. This is our goal. If we can find mass of solvent, then we can solve for the overall molality of this equation. Fortunately for us, again, we already know some stuff about our solute, namely that we've already found how many moles of solute we have. Well, if we know the moles of the solute, and we know the identity of the solute, which is potassium chloride, all we need to do is convert moles into grams, and we've done that calculation like 1,000 times already. So all we need to do is find the molar mass of our potassium chloride and use it to convert out of the unit of the mole and into the unit of the gram. All right, so we can pull out our periodic tables. We would find that the molar mass of potassium chloride is 74.56 grams, meaning that the overall mass of the potassium chloride, our solute, is 350 grams. This is 350 grams solute. And this we can insert now into the equation that we have found below. Rearrange to solve for the mass of our solvent by taking 1,090 and subtracting out 350, and we find a total mass of solvent equal to 740 grams. Well, in the molality equation, we can see that the denominator needs to be in kilograms, so the very last thing that we need to do is convert this gram measurement into kilograms to find 0.740 kilograms of solvent. All right, so again in review, density corresponds to the solution, meaning that we were able to find mass of the solution. In subtracting out the mass of the solute from the mass of the solution, we were able to find the mass of the solvent itself, convert it into kilograms, and now we can insert this into the equation to solve for what we were actually asked to find, the molality. All right, so if we take 4.70 moles and divide that by 0.740 kilograms, what we find is that the molality is equal to 6.35 little m. I know it looks a little strange to see little m for molality is equal to 6.35 little m, where this little m is now a unit, but this is the way that it appears. So again, it looks strange, but we are okay here. This m stands for molality, is equal to 6.35, we would say moles per kilogram, or little m. So in conclusion, we can see that our initial concentration in molarity is close to, but not equal to, the concentration as measured in molality. And this difference primarily comes from the fact that we are looking at a solution that does not have a density directly equal to 1. So there is going to be a temperature dependence here. The volume is fluctuating as a function of temperature, whereas mass stayed the same. So if we were to observe any of the properties which we have yet to talk about, I know it's strange to abstract them like this, but molality is going to be the more consistent unit to use, the most consistent means to measure concentration here. Molality is not the only consistent means, though, to measure concentrations. Percent by mass is also a very, very common practice, particularly in industry, that is used to measure concentrations. So percent by mass, most straightforwardly, is mass of solute divided by mass of solution times 100. We're literally just looking at a percentage here. How much stuff do you have in the total solution where both of your measurements are in mass? So we're not looking at moles per liter, no moles per mass or kilogram, we're just looking at mass per mass. All right, so percent by mass is the percent of a solute's contribution to the total mass of a solution. However, sometimes it is also going to be more useful to not look at percent, which is parts per 100, but rather to look at parts per million, or ppm, or sometimes also parts per billion, which is ppb. Now, these measurements and how we find parts per million as well as parts per billion is the same equation as our mass percent below, but the difference is that in parts per million, we multiply by 1,000,000 instead of 100. So this 100 would be a 10 to the 6 if we're looking for parts per million, or ppm. And similarly, if we're looking for parts per billion, this is going to be equal to mass of solute divided by solution times 1 billion. All right, so there's a couple of scribbles here on the page, but percent by mass can be found in parts per 100, parts per million, or parts per billion. Parts per 1,000 can be found as well. It's just not normally an industry standard. Percent is the most common if we are working with more concentrated solutions, whether they be aqueous solutions or solid state solutions. Parts per million and parts per billion, though, is very common when observing trace amounts of solute inside of solvent. For instance, if you are observing water quality, if you work at like a water treatment plant, hopefully the presence of ions like lead, iron, copper, etc., like the more dangerous species, are going to be in concentrations so low in parts per million or parts per billion, literally at levels low enough where they can do no harm. If you have worked, though, with any type of percent equation, parts per million and parts per billion, hopefully, although again, looking a little bit different in terms of what we're multiplying by, it's not going to be too confusing. So today is a very quantitative heavy day because we are working with concentration units, but in much the same way as our previous example problem where we were looking at the relationship between molarity and molality, in this problem we are going to be looking at the relationship between molarity and parts per million, so one of these percent by mass types of units. All right, so let's find the concentration of a solution in molarity, where the solution we know is a 3.1 parts per million sodium chloride solution, if the solution also is known to have a density of 1.02 grams per milliliter. And again, we are going to assume a 1 liter solution. All right, so we're going to take the same approach as the previous problem, break down what we have present in terms of solute, what we have present in terms of solution, and what we have present in terms of solvent. So since we've already approached this type of problem already today, here I'm going to invite you to actually pause the video and try and work through this problem on your own. All right, so again, we are going to come back together and approach this problem in much the same way as we approached the previous problem today. We need to find a concentration in capital M, and we know capital M is moles solute divided by liters solution. So again, we're going to pay close attention to solute versus solution versus solvent. We are told that the solution has a percent by mass that is 3.1 parts per million, and we're also told the density of the solution. All right, so we can use density in much the same way as we saw before. We're going to see how to approach that in a little bit, but I want to make sure that we're not getting ahead of ourselves. All right, first and foremost, let's observe percent by mass in terms of parts per million. is going to be equal to the mass of the solute divided by the total mass of the solution, all multiplied by 1 million. All right, so here we can start hopefully plugging in some information that we have, if we have it. Well, we know that the parts per million is 3.1 parts per million, so that's cool. We have one side of the equation figured out. Well, we can see that we don't actually have explicit mass of solute in the wording of the problem, nor do we have explicit mass of solution. So we're going to need to find mass of solute as well as mass of solution if we have any hope of finding the moles of the solute. Now, in the wording of the problem, since we are explicitly working to find concentration in moles per liter, we actually already know the volume of our solution. Again, we're assuming 1 liters of solution. So we already know the denominator. Moles of solute here is going to be the tricky thing to find. All right, so let's get cracking. Let's try and find the mass of the solute, the mass of the solution, to actually rearrange and solve for moles of solute. Well, in order to determine which of these two we should be trying to fill in for, let's turn our attention back to the problem. So we know that we have a density of solution as well as a volume of solution. Well, density coupled with volume will give us a mass. The question is, which of these two masses are we going to get? Well, again, just as we saw in our previous problem, the density that is presented is the density of the solution. It says so in the problem. Solution has a density of 1.02 grams per milliliter. So the 1.02 grams per milliliter is going to correspond to the mass of the solution divided by the volume of the solution, which we don't know the mass of the solution. Turns out that's going to be what we're solving for in this problem to find our denominator in the mass percent equation. But we do know the volume of solution, which is again that 1.0 liters of solution. However, before simply rearranging this equation, we have to observe our units, make sure everything we've plugged in works well together, and here we can see now we're sort of misaligned. Our density is in grams per milliliter, volume is present in liters, so let's convert this into 1,000 liters, or milliliters, excuse me. 1,000 milliliters is present inside of every 1 liter. So now we can rearrange to solve explicitly for the mass of the solution. Take 1,000 milliliters and multiply it by 1.02 grams per every milliliter to find 1,020 grams of solution. This is going to be now what we can insert into our parts per million equation back over to the left. Our mass of solute is going to be the unknown variable now that we can rearrange and solve for, because as we can see, we have one complete equation and only one unknown. So we can rearrange this equation by first dividing each side by 1 million, right? We want to make sure that we can move that over to the left. Similarly, divide by a million here as well, cancels out on the right-hand side. In order to then, last but not least, rearrange and solve for the mass of the solute, where we're taking 3.1 parts per million, divide by that 1 million, we're going to have to multiply up the mass of the solution to the other side, which is 1,020 grams. And in taking this ratio, what we find is that the mass of the solute is equal to 3.16 times 10 to the negative 3 grams. Now this mass makes perfect sense, right? It's a small number, and good thing it's a small number because we were measuring parts per million, which is a very small unit. So this is a way that we can double check our math to make sure that we have rearranged everything and solved for the mass of the solute, which is NaCl, correctly. All right, so now that we have mass of solute, again, we can kind of return to the original problem. We're looking for molarity. We can't plug in mass of solute anywhere in this equation. However, we can use this mass to find the moles of solute, which we do need for the equation. So since we have a mass, again, we can use molar mass, as we have done many times before, to convert out of the unit of the gram and into the unit of the mole. the molar mass of sodium chloride is 58.44 grams per every mole. Grams are going to cancel out here, giving us a measurement of 5.41 times 10 to the negative 5 moles. All right, so we can take now this number of moles that we have present, this 5.41 times 10 to the negative 5 moles, plug it into the numerator of our original equation, and again, the volume of solution is just straightforwardly that 1 liter of solution from the wording of the problem. Rearrange, or crunch the numbers rather, and find that the concentration is equal to 5.41 times 10 to the negative 5, capital M for molarity. So the crux of this problem was the same crux of the last problem, being able to ascertain whether or not the values provided correspond to solution, solute, or solvent. Again, as long as we're making sure that we're double checking what the measurements correspond to, we will be able to use the information provided to solve the problem at hand. But that's all I have for you guys today. So it was 2 tedious example problems introducing 2 new types of units, as well as how they kind of work together, but it's totally fine that that's all we're looking at today. There's always that trade-off, how qualitative versus quantitative was the day. Today was very quantitative, and so we covered, in general, very little new information. That's perfectly fine. I would strongly suggest working through the example problems provided here just to make sure that you're able to understand and ascertain for yourself the differences between the masses, volumes, densities, molarities, molalities of solutions, solutes, and solvents. All right, but if you have any questions, particularly because today's math was so tedious and involved a lot of critical thinking, please do not hesitate to let me know if you do have questions. But otherwise, if you have homework, please double check and do your homework. And until next time, class is dismissed.